imagining that today's lecture probably won't go as long as last time. And I'm going to go over the new homework for chapter 11 that I assigned. There's a problem in that homework that I really want to talk to you guys about. And it's weird. I have a suspicion that your book is somewhat wrong. And in fact, a lot of physics books are somewhat wrong in something, and we'll talk about that. Turns out that the problem that I'm talking about when I go over it, the problem's right. And so I don't know, it's weird. We'll get to it, I'll talk about it. It's a really hard problem. And I think a lot of you may find this chapter to be very hard. And so I'm going to try to take you through it. I'm going to try to go through it in a number of different ways to explain what's happening. And hopefully, once we're done with this lecture, I'll go through the homework problems and hopefully it'll make sense. I will tell you that this chapter, Understanding Angular Momentum, ends up being a very small part of solving problems. And then on Tuesday, we're going to cover chapter 12. Chapter 12 is simple. There is something called static equilibrium, and that means that for the whole system, all the torques equal zero. There's no net torque, but there can be a whole bunch of internal torques. If you imagine a seesaw, you could have weights on either side of a seesaw, and those would be torques in equilibrium. So it's super easy as long as you understand torques. It will take us maybe an hour to go through chapter 12. And the second half of chapter 12 is about stress and strain. And some of you are going to love that because that is plug and chug. You literally plug in numbers and you're done. So on Tuesday, we're going to go over that and we're going to introduce, I'm going to post practice exams today after class. I'm going to go over some problems with energy and torque and how to kind of use all this stuff together. So if you're still not putting this stuff together, that's okay. We'll put it all together on Tuesday. We'll have some problems where we really put everything together. Anyway, on to today.
Excuse me.
Yes.
I have a question about the quiz.
Sure.
The first part is says that the ball is moving horizontally. Is it on the surface or in the air?
Yeah, you can think of it just like the IOLAB. It's just a ball rolling.
On the surface.
Yeah.
Okay.
And you don't have to worry about, it doesn't have a moment of inertia, even though it says it's a ball. Assume it's not rotating. I don't know why I said a ball. I should have said a ball. All right, so chapter 11 is all about torque and angular momentum. And so the things that we learned in chapter 10, I want to kind of review those things kind of pretty fast. The first thing that we learned is that if something's doing what's called, the heck just happened? That was so weird. Doing what's called rolling without slipping. And what that means is if it's on a surface, as it rolls, the amount of the distance it travels in one rotation is equal to the circumference. So that has to be true. Otherwise, we wouldn't be able to figure it out, because if it was sliding, there'd be some weird acceleration. But that leads to this S is actually the distance it travels around in meters. And R is the distance from an axis of rotation. In this case, it's the center of the wheel or the center of the ball. And then theta is the actually the change in angle in radians. So if we take the time derivatives, we got that the linear velocity of any point is equal to the radius to that point, and the angular velocity. So what this means is if we had some axis of rotation and we wanted to figure out how some little dm mass was moving. So let's say that this is omega. This v is related to omega by r. And we did that with uniform circular motion. So these things are pretty, we've seen these a bunch of times already. And then finally, if v is related to omega, a is related to alpha. And you can solve those for yourself by taking the time derivatives of each one. It's not
Professor,
yes.
can you remind what omega and alpha was?
Omega and what?
And is that alpha, the little a?
So omega is the angular velocity. It's basically how fast an object is rotating about. So imagine this is a wheel that's spinning clockwise. Omega is how fast it's rotating. The entire thing has the same omega. So every point on a disk has the same omega. However, they don't all have the same velocity. The reason for that is if this is spinning as a solid uniform disk, then what happens is the points closer in have less of a distance. They have a smaller circumference to travel. And the points further out have to travel further, so they have to travel faster. So basically, this is true. What's weird here, though, is v and omega are both vectors, but they don't point in the same direction. So as these points go around, right, v is going to be changing as it rotates. But omega is about this, it's actually about the negative if we're talking right-hand rule. So the reason why I'm not putting like vector signs on everything, we know that v and s and a are all vectors, but they're not in the same direction as r and omega. So it gets really weird. Essentially, r and v are always perpendicular. And yeah, it's kind of a mess. But the big thing to remember is that each point, each little dm, little infinite mass, infinitesimal mass, has a velocity. This is the same for all. So they all turn at the same rate because that is in radians per second or degrees per second if you wanted to change it. But the other thing to remember is that when we talk about a revolution, that means that the object went all the way around once. So for a revolution, delta theta is 2 pi radians. And if you need to convert 2 pi radians to 360 degrees, it's the conversion. You always want to be in radians. Radians are a real number, degrees are not. So what that means is if this is delta theta were 60 degrees, like it went through a rotation of 60 degrees, r times 60 degrees is not a number. 60
pi over 30.
Yeah, it is pi to the third, which is what, 3.14 or whatever. This is about 1. So if r was 1 meter and delta theta was 60 degrees, this would be pi to the third. So you would have traveled a third of pi around the circle. Just make sure that you guys understand that you cannot be in degrees when you're trying to find arc lengths. So that we've covered, that goes all the way back to like chapter 3, uniform circular motion. Although now we're using it for everything. We're assuming everything spins at a uniform angular velocity, or it speeds up or slows down.
What about alpha?
We're getting to alpha right now. So
sorry.
Just like with the change in omega, the change in the angular velocity is equal to alpha t. We can solve these by doing the integrals for what is this, alpha t and I should do this right. Alpha is d omega dt. So this is d omega is alpha dt. And since alpha is considered to be constant, we just get the same ones that we knew before. Angular velocity, Farhan, it's a vector, but the problem with it is that when we talk about the velocity vector, we talk about whether or not it's around some axis. In this case, I'm going to say the axis is z. If this were rotating this way, we would actually say that this, I'm sorry, let me take that back. Right hand rule, your thumb is this z axis. Right hand, your thumb's pointing out of the screen towards you. The way that your fingers curve is the positive omega direction, the positive rotation. So what we say is that omega is a vector pointing along positive z, but it's not really. It's just a nice way to understand which way the rotation works. It turns out that rotation vectors aren't actually totally vectors. And then on the other hand, if omega was negative or clockwise, then by the right-hand rule, if you try to turn your fingers to the right, this would be into the page, negative z hat is what we say. But it's important to remember that we're calling whatever the axis is z hat. I'm just generally calling it z hat. So if alpha's constant, you have the same constant equations. And this will come into play because a lot of times what we're going to do is we're going to find omega. And then we're going to need to, or we're going to know omega. We're going to know how fast something rotated or how slow. And we're going to need to find alpha. I'll show you on the homework in a second. The other thing to talk about is the period. So the period of one revolution, you already know is 2 pi r over v. Since r over v, though, is omega, the period is directly related to omega. And the period is how long, the time it takes to make one revolution. The Earth goes around the sun in 1 year, pi times 10 to the 7th seconds. A top may spin at 0.01 seconds. It's the time it takes to make one revolution. The frequency is the number of revolutions in a second. So it's the inverse of the period. Just so you know, those are just definitions we may need for something we're doing. So let's go to the homework really fast. This is homework 10, chapter 11. And the first couple problems are just for you to understand angular acceleration and whatnot. So you're given that an automobile is traveling at 58 kilometers per hour. That you're going to need to turn into meters per second. That's, did I? Oh yeah, sorry, this is initial. Whoops, typo. So if you turn this into kilometer per hour into meters per second, and the tires have a radius of 67 centimeters. So let me talk about this really fast. What was it, 56 for me? It'll be something different, 58 for me. So 58 kilometers per hour. Remember that there are in 1 kilometer, there are 1,000 meters. And in 1 hour, there are 3,600 seconds. So this ends up being 58,000 divided by 3,600, about 16.1 meters per second. And we were given R in centimeters because that's what Wiley does, 67 centimeters for me. So that's 0.67 meters. So this is actually your V, and this is your R. Remember that V is equal to R omega, and A is equal to R alpha. Now, this problem says, what is the angular speed of the tires? It means omega. So you would just take V and divide by R. If the car is brought to a stop uniformly in 31 complete turns, what is the magnitude of the angular acceleration? So 31 revolutions is equal to what? Well, 31 times 2 pi radians. That's delta theta. Omega final will be 0 because it comes to rest, and we want alpha. And we know what omega initial was. If we find it here, omega initial would be V over R. So for me, that would be 16.1 divided by 0.67, so 24.03. This is my initial. I was also given time. No, I wasn't. I was just given delta theta. So again, if we know delta theta, we know omega final and omega initial, and we want alpha, we can just look back at these and look at the ones that have the ones we need. We don't have time, so we'll use this bottom equation. And that bottom equation says omega final squared minus omega initial squared is 2 alpha delta theta. And you can easily do that, solve that for alpha. Notice it'll be negative, which is fine. It's coming to a stop. It's slowing down, it's rotating less. And then how far does the car move? That is just using S is how far, stop, R delta theta. So once I know R and delta theta, which I do, 31 times 2 pi rads, I can figure out how far it traveled. Hopefully that makes sense to you. So this first question should make sure you guys understand that. This second question I'll come back to. I thought these were all, nope. So, okay, so just make sure you understand uniform circular motion variables, rotational variables, and how they're related to translation variables. The next thing we need to remember is that there was a new kinetic energy associated with a rotating object. That was moment of inertia times angular velocity squared. Yeah, this is homework from a totally separate Sammy. This one I posted, I was asked to post yesterday. It's not due until the day of the exam, so you have plenty of time. It's brand new homework. Kinetic energy of rotation is moment of inertia times omega squared over 2. And you know linear kinetic energy is mv squared over 2. We also know that for point particle, I is mr squared. And since omega is v over r, this and this are related because I omega squared can be turned into mr squared times v over r squared over 2. R's cancel and this becomes mv squared over 2. So the rotation kinetic energy and the translation kinetic energy of a particle would be exactly the same. I omega squared over 2 would be different if the moment of inertia is different. And any solid object has a given moment of inertia. Last time we calculated a few of them, like the thin rod about the center. You have to differentiate between a center of mass axis. So imagine you have a top. If it were rotating about here, about its body axis, that's a center of mass rotation. If it were for some reason rotating about here, that is not the center of mass. That is a different axis. So most of these have a definite symmetry, like a hoop. If a hoop is rolling, like a wheel would roll, then it has the same moment of inertia of a particle. If a solid wheel is rotating, it's I equals mr squared over 2. The reason why the moment of inertia is smaller for a solid object instead of a hoop is a lot of the mass is concentrated to the center on the axis. And we already know that things that are on the axis don't have any torque. We'll talk about that if that's not clear already. But so what you do in practice is you go to page 274 and you look up what the moment of inertia is for your particular object. Maybe it's a door swinging and you want to know what the moment of inertia is for a rectangular, thin rectangle about one edge. That's in your book. The other thing to remember with moment of inertia is the total moment of inertia is equal to all the moments of inertia added together. So if we had like 7 little balls all stuck together, we could get the moment of inertia if they were rotating. We would have to use the parallel axis theorem. And we showed this for a thin rod. So a thin rod, if you're rotating it about its center, right, it has a moment of inertia of ml squared over 12. If you're going to rotate it about one end, however, how do you find it? The answer is this parallel axis theorem. This says that the center of mass moment of inertia plus md squared, where d is the distance we move the axis. So we're moving this axis parallel to the original center of mass axis by a distance of L to the half. If this whole thing is L, then this is L to the half. So this becomes m L to the half squared, which L squared over 4, this ends up being mL squared over 3. So that's a second way that you can find moments of inertia. And in fact, you end up needing to use it. There's a problem in the last homework where you had to use 2 rods and 2 balls and find the moment of inertia about one end. You need to use parallel axis theorem quite often. We're going to use it a couple times today. And then we also talked about torque. And with torque, you can imagine that if you have, say, a ball on a massless rod at a distance r from some center of rotation, and you apply a force pushing down on it, this F crossed with R, how we draw that is you put R and F tail to tail. The torque is always R turning to F. Because it's counterclockwise, that's positive if we assume this is the positive alpha direction. And therefore we get R cross F. R and F in this case are 90 degrees off each other. So this would be 90 and sine of 90 is 1. And we know it's in the positive Z direction. We'll talk a whole bunch about torques today. But torque leads to rotation. And how it leads to rotation is torque is equal to I alpha. Alpha meaning angular acceleration. So torques cause rotation. And if there's no torque, the object doesn't rotate. Actually, what we really should say is there's no external torque, the rotation doesn't change. But most of the time, we're going to talk about just rotation. And then finally, the last thing that we need to know is that I alpha is equal to the net torque. So this is all the torques. You add them all up, just like we add up forces, just like MA is equal to the sum of the forces in whatever direction. I alpha is equal to the sum of all the torques. And we'll see that today too. The kinetic energy or work, the change in kinetic energy, is equal to the torque times delta theta. If you do this, if you multiply by I alpha, which is what torque is, times delta theta, you get 1/2, or I, remember the kinetic energy is I omega squared over 2, so I omega final squared over 2 minus I omega initial squared over 2. But if we go back to this equation, multiply both sides by I and divide both sides by 2, and the 2 cancel, and you get this equation flipped around. You can derive that directly from that constant acceleration equation, which is really nice. But you could also derive it from the work by doing that the work is the change in rotational kinetic energy, which is equal to torque times d theta. It's in your book. It's not hard to do. Assume that the torque is constant and it comes right out. We also talked about that last time. So I know that's a lot of stuff to talk about. Hopefully, as we start doing these problems today, this stuff will start making a lot more sense. So, rolling and translation. So I want you guys to pay a lot of attention to this. I mentioned in the pre-class that there's a problem with one of the examples in here. And it's a problem that shows up in every physics book, it looks like. And then I gave you a homework problem that directly refutes it. And this is going to go a long way to understanding what the problem is in that problem. I don't know if I've showed you this before, but imagine a wheel that is rolling and it moves so it rolls until it gets to this point, right? Every single little slice of mass, and I'm just going to put the four corners and the center, has the same velocity to end up getting over there. So the translational velocity, the straight line and the x velocity, is the same for every point of mass. You have to imagine that it's, you gotta kind of imagine that you're at rest on the object and you'll see that it goes. However, if it's rotating, it also, each of those has a rotation velocity due to the rotation. At the top, it's the same as v. At the center, it's 0. And at the bottom, this little mass is going to be rotating backwards. This one will be down, this one will be up. So make sure you're clear on this. Because it's rotating, at the edge at those 5 points, the velocities are shown. And that's not too hard to see. But that's the rotational velocity. And the actual velocity of each point is a combination of translation and rotation. And we're going to see something really weird happens when we do that. Now, if it's translating v, and I'm just going to show you, I don't care about the middle one. I mean, and I just did that backwards, sorry. I'm just going to show you one side of this. And now I'm sorry, at the top point, v is in the same direction as v. So this one is the translation, this is the rotation. At this point, it's down. At the center, red v, rotational v, is 0 because it's at the center, it's not rotating. And at the bottom, it's in the opposite direction. If we assume that v from rotation and v from translation are the same, which they are, then look what happens to the velocity of these points. You end up with 2 times v. Let's say v was 1 meter per second. The top point is moving at 2 meters per second. The middle point is moving at 1 meter per second. And the point at the ground is not moving. There's a point on a rotating object where it's on a surface. There is no instantaneous velocity. Much like when you go up in projectile motion and drop back to the ground, your instantaneous velocity at the top is 0. There's an instantaneous velocity at the point of contact that's 0, and that will become important later. But if you don't believe this is actually true, I want to show you a picture. If you took a picture of a wheel rolling, a bicycle wheel, let it roll on the ground. You take a picture, and in that instant, if I'm not clear, this is what I'm trying to show you, that pure rotation, pure translation, and if you add them together, this is what you get. You get 0 at the bottom. This is a picture of a bicycle wheel rolling, and you can see that it's not really an optical illusion. The picture is much clearer at the bottom because it's not moving, it's not blurred. It's a very real effect. The top of the wheel moves faster than the bottom of the wheel. Really strange. Really, really, really strange. It's a weird consequence.
Professor.
Yes. Go ahead, Lucas.
So, going back to the picture you just drew, so what you drew in red was a rotational velocity, right?
Yeah. So in this picture, it's the part A.
Okay. But why what I'm confused about right now is why is it once it rotated, did it rotate 180 and then the top
No,
velocity
no.
was 2v?
Just assume it's constantly rotating right now.
Okay.
And you're
So why is it
looking at a point on the wheel
uh-huh.
that's at rest, which is weird. There is actually a point that is instantaneously at rest at all times, and that's the point where it's in contact with the surface.
Yeah.
It's weird. Trust me, it's weird. But we're going to use it in a little bit. I just want to make sure that you guys understand this is actually true. It's not a weird mathematical concept. You can actually prove it by taking photos of bicycle wheels spinning, or any type of spoked wheel that you can see spinning. It's really odd, but it's kind of neat. It's one of those weird physics things.
Why is it 2v though?
What is that?
Why is it 2v though? Like I'm
Because it
confused on
has translational velocity and it has
uh-huh.
rotational velocity. It's both
Oh,
and translating at the same time. I know it's weird that it would have that it would double it up, but it does.
so it's like twice as fast as the
So,
translational velocity?
so look at the top here. You can't even see the spokes anymore at the top
Yeah.
because it's
Uh-huh.
moving so fast. Yeah,
Yeah. Okay.
it's a
So
real.
it's kind of like you added.
There's also a weird phenomena, if you guys have ever noticed this with like spinner wheels, that you'll be looking at them and they seem to be spinning backwards in the wrong direction. That's an
Oh
optical
yeah.
illusion of your
Okay.
eyes. It's weird. Your eye like actually starts picking up the frequency of how it's spinning. Odd stuff. But this
Kind of
is
like when you flick a coin, right? Or I'm trying to think of something that's like rotating and then it kind of starts it's kind of like it's rotating backwards like
yeah.
I don't know why though. But yeah,
No,
I know
yeah,
what you're talking about.
this is much like the nearest thing I can equate this to is in projectile motion when something goes up right at the top for an unmeasurable moment in time, an instant in time, the velocity is 0. And so for an unmeasurable moment in time of the wheel at the bottom, the velocity is 0. It becomes important though for us because mathematically, anytime we can find something that's 0, as physicists, we want to exploit that 0 as much as possible, because we definitely know what the value is there. And we're going to talk about this in a little bit, but it doesn't affect anything. It's just that there is a point that is 0. And so we'll talk about that. The other weird thing is if you look at this, so this is actually the velocity vectors of the different points on the wheel. And that's really odd. I should also say that these velocity vectors only make sense if you're standing at the point P. If that's your frame of reference is the point P, then you see these velocity vectors. Really odd that a solid wheel everything has different velocity vectors, and it's just really hard to figure out, to be honest. It's not easy to figure out what exactly is going on. You have to measure these R's, and the nicest thing though is this big mess that you look at and you go, there's no way I could figure out what that is. What's really nice is it's a combination of these two things. And if you add them together at each point, like here, it has double V. Here it has some translation and some rotation and no translation, you know, blah, 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 blah. Or they're equal, I should say, and on and on and on. It's a weird idea. We don't assume the vectors are at 90 degrees in general. They're just there because that's the easiest to see in this picture, I think, is what you mean, Sammy. Okay, so as I said, that's just for later. I want to talk about our first real actual torque problem. If you guys don't know what a yo-yo is, a yo-yo usually is like two discs together with string around it, and you like put the string over your finger and it rotates as it unspools. So it goes down, it unspools, it grabs the end, and it comes back up. We're not going to talk about the dropping to the bottom and coming back up and why that happens. We're just going to talk about a yo-yo falling. And we're going to imagine that it's just a pulley that somehow has a string at the edge. So it has a string connected at the edge. About its center, when it falls, it's going to rotate down. I actually drew that on the wrong side, so I want to go on the other side. And I'll talk about why I do that. So as this thing rotates and unspools, as it drops down the string, let's look at the forces on this. It's got to have a tension from the string up. So this is just the mass of the yo-yo, and it has to have a weight down. And it's going to accelerate downward, right? So we know how to do that. That is MA is mg minus T, or T is mg minus MA. That part's just a free body diagram. Even though the tension and the weight are offset, we only care about the y direction. And in the y direction, it's T is up, mg is down, but because acceleration is down, we can write that. Now, however, we're going to have to write the torque. And the torque on this thing is like this. We know there's a force. It's going to rotate about this axis, okay? And I'm going to say that this alpha is in the positive direction. We know that there's a force, which is a tension, and we know it's at a distance equal to the radius of the yo-yo. So how is this a torque? Well, torque is R cross F. Putting R and T, tail to tail, and rotating R to T, we see this is a positive rotation, so this is a positive torque. R and T are 90 degrees off, RF sine of the angle between them, but that's 90 degrees, so this torque is RF, or better yet, RT. Now, when we write the torque equation, just like we write MA is sum of the forces, here we write I alpha is sum of the torques. There's only one torque here. Why isn't gravity producing a torque? If we look at this, gravity is actually acting at the center of mass, which is where our axis of rotation is. R is equal to 0. That is super important. There is no torque due to gravity because it's literally acting at the center of mass. There is no radial vector. Another way to say that is that the center of mass, or the force of gravity acting on the center of mass, can't cause it to rotate because it's not offset from the axis. I hope that makes sense. It can't cause rotation. It can cause acceleration. It's in fact what's causing it to fall. And the torque is due to the tension at the radius. So this becomes RT. We already said that T was mg minus ma. So we can write R is mg minus ma, or RT is R times mg minus ma. And so what we're left with, when we do this, we're left with I alpha is R times mg minus R times ma. And we have alpha and A. If I gave you R, you would know that I, because this is a disk rotating through its center, if you look on that page 274, for a disk, solid disk rotating through its center, I is mr squared over 2. So we know I, we know R, let's say we're given R is 0.2 meters, 20 centimeters. We know G, and the mass of this thing is, let's say 2 kilograms. We then have two things that we don't know. We have alpha and A. So we have the angular acceleration and the linear. And this becomes I alpha plus MRA is equal to MGR. I'm going to put, now, we can either solve for A or alpha. We know that A is our alpha if we're assuming rolling without slipping. So let's plug in for I, mr squared over 2. Let's plug in for alpha, A over R. So I get mr squared over 2 times A over R plus MRA. Now, this becomes mr to the half times A plus MRA, which is 3/2 mr times A. So if I plug that in here, this becomes 3/2 mr. A is mgr. I can cancel this stuff and I can move that over. So A is 2/3 G in this case. Now, notice that doesn't depend on anything but the moment of inertia of the yo-yo. So if the yo-yo had a different moment of inertia, if the yo-yo was somehow made of, I don't know, a sphere, you would have to find the new moment of inertia and solve for it. And then basically, A would only depend on the inverse of the coefficient of the moment of inertia. That's really strange. It doesn't depend on the mass, doesn't depend on the radius. No matter how big a yo-yo is, it's going to have the same acceleration as long as it's made of a disc or a wheel. That's really, really, really kind of cool. Really cool to know. Kind of odd, but the 3/2 came from I alpha plus MRA, Sam. So I for a wheel is mr squared over 2, and alpha is A over R. So if you plug those in here, you get mr squared over 2 times A over R. 1 R cancels, and you get mr to the half times A plus mr times A, which is 3/2 mr times A. But the MRs will cancel on both sides. And then in order to find G, you just multiply by 2/3. Yeah, I just simplified. Okay, so that's a yo-yo. Now, I want to talk about one quick thing about this that I made an assumption. What if instead of what I just did, I had the tension on the other side? So now the tension's on this side. And this is going to mean that this is going to rotate that way. Let me draw it a little bit better. This is going to rotate negative alpha is what we usually say because it's rotating clockwise. So my force is up, R is that way, tension is up, and this is also a counterclockwise torque. So I would write I minus alpha is equal to minus RT, but they cancel, as they should. So as long as we are consistent with our alpha sign, this is actually one of the places where things get really messed up. These things have to be the same. And right now we have one torque, so it's easy. We only have one torque causing the rotation. It better have the same sign as alpha. Otherwise, you've done something horribly wrong. But what if there's more than one torque? And if there's more than one torque, you need to decide which way is it rotating and what the sign should be. And your signs need to be consistent, meaning if you're saying this clockwise rotation is negative, then every clockwise torque acting on that object is also negative, okay? And if you're saying, let's say counterclockwise, you're deciding is negative, then every counterclockwise torque better be negative, every clockwise torque better be positive. But the idea is that it should give you the same no matter what side of the yo-yo you're on. You better get the same answer with the same sign. So it's a little weird. The yo-yo is discussed in your book. It's given a whole section of its own. So now we're going to talk about the problem that I foreshadowed earlier, which is actually related to the yo-yo. If you need it, here's the whole breakdown of everything I did. So the problem that I wanted to talk about, the problem that's in your book and that's in every physics book, I think, is rolling down an incline. Okay, I'm going to come back to that slide with what was written. But you know how we say that if something rolls down an incline, right? So it's heading down and it's rolling. Can you roll down a frictionless incline? Will a ball roll down a frictionless incline? And the answer is no. In order for something to roll, there has to be friction. If it's on a surface and it's rolling, it has to have friction. So in our normal turning things to the side way, we're going to say that there must be a normal force, mg cos, mg sine, A is going to go that way, and normally we're going to say that there's friction, right? So here's the way your book does it, and then I'm going to talk about this after we're done with this. So there's friction at the base here. If you do just the normal Newton's equations, you get max, may, of course y is 0, x is mg sine theta minus the force of static friction. It is static friction, and we'll talk about that in a second. This would be n minus mg cos theta. Why is it static? So remember we said that that point right there wasn't moving? We are saying that there's some force of static friction that's actually pushing backwards, which is causing it to rotate. For now, let's leave it at that and see where we get from this. Now, if on the center of mass, you have a normal force acting, you have mg cos acting, the weight and the y, you have mg sine acting, and then at this little distance r, you have the force of static friction acting. Which of those is going to be a torque? Well, the only one that can cause rotation is the static friction. The rest of them are acting at the center of mass. So I alpha, if we're assuming this is rotating in the counterclockwise, which is the traditional positive, we would say that there's an R, there's a force of static friction, and this thing's rotating positive alpha. So remember, draw R and F, tail to tail. R turns to F, so that is also the same direction. We write I alpha, sum of the torques. Here it's RFS. So now, from all of this, we can just plug in here I alpha and move it over. So we would get MA plus I alpha is equal to mg sine theta. Let's turn this into alpha. A is equal to R alpha, right? Since A is equal to R alpha, and therefore alpha is mg sine theta times, sorry, that looks bad, times mr plus I. We can do one more thing here, which I'm going to do on a brand new slide. So we got that alpha was mg sine theta mr plus I. Yeah. Now we know that I have something wrong here. Oh, I'm sorry. I have to divide this by R. This is Fs is I alpha over R. So I need an R there. And if I multiply through by R on both sides, this R goes away, this becomes R squared. And that's right. Okay. So I get mgr sine theta, mr squared. Now, I know that mr squared over 2, if this is a wheel, that's I. So let's divide through by mr squared over 2 and mr squared over 2. So really what I'm going to do is, well, let me put it this way. If I divide through by mr squared, and 1 over mr squared. So dividing through the top, I would get g over r sine theta. Dividing through by the bottom, I would get 1 plus, this is mr squared over 2, divided by mr squared, which is a half. So I would get that alpha is g over r, and I still feel like I've got something weird happening, but I'll fix it in a minute. Oh, no, it's absolutely fine. 1 plus 1/2, which is, this bottom is 3/2, so this is 2/3 g over r sine theta is alpha. Okay. Now, what is A? Well, A is R alpha. So if I multiply both sides by R, A is G sine theta with 2/3 in front. 2/3 G sine theta. That is A. Now, on the incline, if the incline were inclined at 90 degrees, what would A be? Sine of 90 is 1. So if this incline were so great that it was essentially 90 degrees that this thing was trying to fall down, you would get the yo-yo. It would be A is equal to 2/3 G. If it could rotate as it fell, the acceleration would be 2/3 G. Only if it's rotating. That's really weird. So going back through this, I flipped it on its side like normal. I got MA is mg sine theta minus f of s, and N minus mg cos. And then the only torque was this static friction at a distance of r. And then solve this equation for Fs. So Fs is mg sine minus ma. I alpha over r, so Fs is I alpha over r. And if I write I alpha over r and then I multiply by r on both sides, I get this.
Professor, what happened to the cosine?
Where? This-
The mg cosine theta.
we don't need it. It just tells you that the normal force is mg cos, but we don't need it in this case. You would need it if we wanted to say that, let's say instead of just Fs, we wanted it to be mu n. So we could actually plug in mg cos theta there, like normal. But we don't need it in this case. In this case, what we did was we had Fs was I alpha over r. Does that make sense?
Yes.
Okay. So in this case, so now if I divide through by r, so that would cancel. And then I move MA over and I turn this alpha into an A. So alpha is A over R. I get this. And from that, I get this, which is, so this is how it's usually done in every physics book. They do this incline issue. However, I have an issue with this, and I want to show you what my issue is. If this thing is rolling, so we really have to imagine this is rolling down, right? You have this ball that's rolling, or wheel that's rolling this way. So on the surface, this is actually moving to the right. And so our force of static friction, which is there to keep it from sliding, it's rolling without slipping, has to be going the other way. Now, those two things had better balance each other out so that there's no force acting at the bottom. We've already seen that. So if that's the case, we don't have a torque. And that's a problem. Now, granted, what you're going to find is that there better be a torque no matter where you put the axis. We're going to talk about that when we talk about chapter 12. But let's do this weird little dance here. What if instead of placing our force here and our rotation axis here, what if instead we put our rotation axis at that point that we know is not moving? So at the center of mass, we have mg sine theta, and we do have mg cos, and we do have and we do have n, but this is at a distance r. Now, we're moving our parallel axis down a distance r. And the parallel axis theorem said I center of mass plus md squared. So our new moment of inertia for this, for a wheel, is mr squared over 2. And we moved it down a distance r, so this is mr squared, not over 2. If I add these things together, I get 3/2 mr squared. And now, looking at this, my torque is actually r and mg sine theta, which is positive. And if this is rotating this way, it's positive. So now I have I alpha is mgr sine theta, where I is 3/2 mr squared. So let's turn this into alpha is a over r, mg r sine theta. So A is mg r squared sine theta over I, which is 3/2 mr squared, which becomes 2/3 g sine theta, which was exactly what we got before. Not coincidentally. It had better give us the same answer. It's one of the things we're going to find in chapter 12, that no matter where we place the axis of rotation, we better get the same torque, the same net torque. If not, we've got something wrong with our problem. And so I guess the books are right that the force of friction does go that way in their picture. And in this picture, it cancels out completely, or it does go that way in this picture. And because it's on the axis of rotation in this one, nothing, there's no torque due to it. I don't know. It's weird. I will tell you to do it this way. Do it this way, the way they show it in the book. It's probably right, and it's probably just me having a weird issue with it. But my issue is that I think they have the static friction force backwards. And I'm going to show that to you, where in the homework problem, they actually do flip it. But this is the way, this slide is how it's presented in every general physics book. The other thing I want to make sure you understand is if you write down just this formula for an object rolling down an incline, in your book, they just give you this with a negative sign. The negative sign is there because in your book, they take A to be positive up the incline. So when I did this, instead of A being down, they have A being up. And it just flips the sign on everything. So this would be Fs minus mg sign. But let's look at this homework problem I have for you guys. I believe it's the final question. This question is tough. If you aren't here for lecture, this question, I guarantee I'm going to get a bunch of people texting me and asking me about this one. So we have a ball. It's being pulled by this fishing line that has some force applied here. And so there's a force being applied at the top, and it's rolling. And it's rolling without slipping, meaning there's static friction down here. So I want to show you this. So if we look at this guy, there's a force being applied here. At the center of mass, there's a normal force up, and there's an mg down. And then in order to actually be rolling without slipping, we're going to assume, just like on the incline, that Fs went that way. We'll assume that A is this way. Now, in this particular problem, and what makes this so mean is they tell us F, and they tell us the mass and the radius of this cylinder, okay? They want to know the acceleration of the center of mass, the angular acceleration, and the frictional force acting. So they gave us F, they gave us M, and they gave us R. All right, so let's start our normal way. MA, and I'm going to leave off N and MG. So MA is F minus force of static friction. And the torque here about the center is at a distance R, there's this force. And at a distance R, there's this force of static friction. We know this thing's rotating this way. I'm going to call this positive. So let's redraw these, R and F. Turning R to F, this one's positive. Turning R to Fs, this one is negative. So I alpha is RF minus RFS. However, if you had wanted to say that this was negative, then this one would be negative and this one would be positive. and I would get I alpha with a negative sign is RF with a negative sign plus RFS. So the negative signs would flip and I would just get this. So I start here. And I want to know what is A, first of all. Remembering that alpha is A over R, I can solve this by dividing through by R and changing that to A over R. So this is I A R squared is equal to I divided by R. So Fs is equal to F minus I A over R squared. And then I'm trying to solve for A. So MA is equal to F minus IA R squared. And I have a problem. I have a really big problem. This doesn't work. If you look at this, this becomes 0. This becomes positive, so I have MA is IA over R squared, and A goes away. So what am I supposed to do here? How am I supposed to solve this? Well, turns out there's an easy way to solve this. So let's go back and look at this. If we have this F and we have this Fs at the center, we can actually move this to here to get the torque, all right? So if we move this by the parallel axis theorem, again, mr squared over 2, and we're now moving this down, so plus mr squared. We're moving it down by r. When we do the torque of this force, this is now 2r. That force is now 2r away from our axis of rotation. Again, we'll say this is alpha. So F and 2r. And this is also positive if we're assuming clockwise, in this case it's positive. So I alpha is 2r times F. And now we can change alpha. Alpha is A over R, and I is, from up here, 3/2 mr squared. So we get 3/2 mr squared divided by R times A is equal to 2RF. If I move the R over, these R's cancel away, and I get that A is equal to 4/3 F divided by M. So now I have A, 4/3 F over M. Let me make sure that's correct. So 4/3 times 19.6 divided by 11.4. I get 2.29239. Yep. So that is A. It wants the angular about the center. Well, the angular one is just alpha is A over R. So if I divide this by R, I get A. And then it wants Fs. And now Fs, going back to MA is F minus Fs, right? MA, Fs is equal to F minus MA. Now RA was 2.239, right? And our M was 11.4. And I'm sorry, our F was 19.6 and 11.4. Stop. Now, look at this. F is 19.6 minus 11.4 times 2.239. You can already see that Fs is going to be negative. What does that mean? Well, let's just do it really fast. 19.6 minus 2.2, 9239. Whoops, 19.6 minus 2.2923 times 11.4. I get minus 6.5-ish. What does this mean? Yep, it means it's going the opposite way. It means that in our model,
So weird.
where we said that it was going this way and F was going this way, we're wrong. F of S actually points that way, which is
So why
exactly,
does Wiley do it like that?
I don't know. Actually, Wiley in this problem is correct. I believe it's correct. The whole point of the static friction is to stop this thing from sliding. Imagine you tried to spin a wheel on ice, right? No friction. The wheel would just spin. It has to have friction to push back on the wheel to make it actually be able to roll. And that static friction has to point in the opposite direction that the wheel's traveling across the surface. It's weird. I don't know. I don't know.
But why is it moving to the right?
I think that this might be a case where the physics books actually might have it wrong, and it's not caught because it's effectively zero right there. It's weird, very weird. But anyway, I just want you guys to think about that when you do this problem. The only way to do this problem is to move the axis of rotation down. When you do that, you're going to have to re-find the moment of inertia of this wheel using the parallel axis theorem and moving it down to the bottom point. From there, remember that the force is now at 2r, the lever arm of the force. The radial arm is 2r now. And from there, this problem's pretty simple. The hard part is that. Yeah, it's really bizarre stuff here. I don't know.
Professor,
Yes.
when we're drawing the, I forgot what it's called, like our modified free body diagram.
The torque diagram?
Yeah, the torque diagram. So we write I alpha and then we cross the radius with the force, right?
Yeah. So what I want to see from you guys is, let's say we have a pulley and we know the pulley's rotating this way. And let's say there's a tension 2 and a tension 1 hanging on. So you know this is R, right?
Mm-hmm.
This is also R. But let's say we're going to assume, or you just assume, you assume that this is positive alpha. So when you draw your torque diagram, you draw R and you draw the force tail to tail, and you turn R to T. That's what the whole point of the vector lab was about, was making sure you guys understood turning A to B. The torque is R cross F, A cross B. You turn vector A to B. Now we look here, and you've told me at the beginning that counterclockwise was positive, this one's negative. Over here, I have R and I have T1. This is positive, same direction as alpha, right? And since they're automatically 90 degrees off, then the sum of the torques is I alpha plus, and I get RT1 minus RT2. That's the whole point of drawing these diagrams, is so that you can write that equation using the diagram. But I want to make sure that you show me why the torques are positive or negative. That's the whole point, Lucas. Does that make sense?
Yeah. So like in this case, since we have two tensions, you would write T1. It would be T1 minus T2 because it's negative on tension 2.
RT1 is positive, RT2 is negative.
Oh, okay, got it.
And we're going to do more of these. We're going to do things like we'll have a like a scaffold that's being held up with like a mass here. This would have a tension 1 and a tension 2 and an MG, and then the whole scaffold's MG would be pointing down. But if this is our axis of rotation, you would actually end up with 3 different torques here, all on the same thing with different R's. So call this R1 and R2 and R3. So
Mm.
to do that, you're going to have to draw 3 torque diagrams. And you can see that this one, this T1 would be causing it to rotate that way, right? And this T2 would be trying to make it rotate that way. And this would be trying to make it rotate that way. So you have to be careful with the signs on your torques. We'll talk about that next week, but it really comes down to making sure that you're consistent with your signs. So if you decide that this thing is rotating counterclockwise, this torque has to be positive and this torque has to be negative. It's like this tension is keeping it from rotating counterclockwise. Does that make sense?
Yeah.
So, but what if you told me, oh, well, I think it's going to rotate clockwise? I'm totally okay with you saying that this direction's positive, so this one's positive and this one's negative. But you have to, just like when we do the free body diagrams, where you have to choose A, you have to choose alpha in one direction or the other to be positive, and then everything has to be consistent to that. Otherwise, you'll have mistakes on your signs in your answers.
Yeah.
Cool. All right. So we're going to talk about the fun stuff now. That was all the garbage stuff. Before I do that, I wanted to look at this really fast. So this problem here is an energy problem. We'll talk about it next week. If you're trying to do it on your own, this is a solid ball. You can assume that it has rotation and it has rotational energy at every point. So do it just like we did the rotation or the other energy problems, but add a I omega squared over 2 term. And remember to make sure you use I for a solid uniform sphere. Not too bad, actually. This is a yo-yo problem. We just did a yo-yo and the yo-yo is basically solved for you in the book. Okay, so now we need to go and talk about other stuff.
Are you making chapter 10 and 11 homework due on the same Sunday?
I think chapter 10's due the Sunday before the exam and 11's due after the exam and 12's due after the exam.
Okay.
So
The chapter
11's due basically 2 weeks from today.
yeah, but it's chapter 11 will be on the exam though, right?
Oh yeah, and 12 will be on the exam. It's all energy, momentum, and torque. So you'll see on Tuesday when we start doing energy with rotation, all it boils down to is adding another term. Okay. It's weird, but okay. So momentum, linear momentum, and like your quiz today. Why do you do that to me? It must be how I hit my hand on my tablet. So if a block is sliding with some velocity, we know that it has kinetic energy. We know that it has linear momentum. And we saw that another way we could state Newton's second law is that force is the time derivative of momentum. So F is d mv over dt. If we assume mass is constant, this is dv dt. But what's nice about that is if there is no external force, then we have no change of momentum, which means P initial is P final. And if we had multiple objects, we could, if we had multiple objects, we could add the momentums together, the initial momentums and the final, and blah, 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 blah. Also, kinetic energy conserved if there's no external forces. And we see that in elastic collisions where they bounce off each other. So we need to figure out, well, if that's true, maybe there's momentum when things are rotating. And we know that the kinetic energy, much like mv squared, is I omega squared over 2, and that the momentum was mv. So what if we assume that I omega is the momentum for rotation. And we're going to call that an angular momentum. Well, turns out for a point particle, I is mr squared over 2, or mr squared, and omega is v over r for rolling without slipping. And if we put those in, so we get I is mr squared, omega is v over r, 1 power of r cancels, and we get mvr. This is a quantity that we call angular momentum. When something is rotating, quote unquote, and I'll talk about that in a second, but when something is rotating, it has momentum associated with rotation. You can see that the units here would be kilograms, meters per second, times meters. So they're kilogram meters squared over seconds, which again, remember normal momentum is kilogram meters per second. Now we have an additional meter term. So angular momentum actually has a little bit different units than normal linear momentum. It has an addition of m because of the r. Well, it turns out the proper mathematical way to describe angular momentum is we're going to call it L. They pick little l for angular momentum. It is a vector, but it's the cross product of r and p. What that means is it's a quantity that depends on the perpendicular portion of r times the linear momentum. If that's all goobly goop to you, imagine we have a mass and it's traveling in this direction. So P is mv, and it would be in the y hat direction if this is y and this is x. Now, about a point, let's say a meter to the left, there's an r vector in the x direction. So r is in the x direction, and let's say it's 1 meter actually. So r is in the x direction and momentum, linear momentum, is in the y. And if we cross those two, what happens? Well, if you remember, there's no z component in r or p, and the cross product a cross b, if there was no z component to either one of them, ended up being ax by minus bx ay in the z hat direction. Well, we have here p is b and r is a, so we don't have this term, and r cross p would give us mv, and let's just call this little r, mvr in the z hat direction positive. So what that means is angular momentum is just like a torque. You draw r and p tail to tail, and you turn r to p, and you get an angular momentum vector along this weird z direction. Now, that also means that, like any cross product, you get mvr sine of the angle between r and p, z hat. That's same as torque. The weird thing about angular momentum is right now, I'm on the Earth and I have angular momentum about an axis of rotation going through the body of Jupiter. Why? Because I'm moving at some distance from the axis of rotation. So angular momentum depends on what axis of rotation you're talking about. As a general property, it's not super useful. When it's around a specific axis, we can say that a body has an angular momentum. We talk often in quantum mechanics about the angular momentum of electrons because they're rotating. They have, about the nucleus, they have angular momentum. In fact, they can have only two values, positive or negative, implying which way they're rotating, which is kind of weird, but if you think of an electron as a particle or orbiting the nucleus of an atom at a distance r, then it can either be rotating clockwise or counterclockwise. So it can have one of two values of angular momentum. The total angular momentum for a system. So imagine now that I have about this z-axis, I have two masses rotating. They're both at r, right? This one's got b in the negative y direction, and this one's b in the positive. They're rotating around. What is the total angular momentum? Well, this would be negative mvr, and this one would be positive mvr, both about the z-axis, right? Or no, because this is also negative, these both become positive. So I would get 2 mvr about the positive z. And you can see that if you draw the torque diagram. R mv, R mv, this one's turning positive, this one's turning positive. They're both turning clockwise. They both have positive angular momentum, and we just add it together to get the total of the system. I hope that makes sense. One of the really nice things that we've already seen is that L is equal to the total moment of inertia of the system times omega. In this case, what is our total moment of inertia? Well, it's mr squared for one mass plus mr squared for the other, right? So this equals 2 mr squared. What does omega equal? V over r, and this becomes 2 mvr, just as we've already found from torque. So angular momentum, there's something called a total angular momentum of the system, and that's equal to the sum of all the little angular momentums, but you have to choose an axis of rotation to be talked about. And normally with like a wheel, we're talking about the center, right? So what you would do technically for a wheel is you would have to add up the angular momentum of every little mass in it, but that would just give you the moment of inertia of the wheel, which we already know about the body axis, mr squared over 2, and omega, where omega is the angular velocity of the entire wheel. Not bad. Yes. Go ahead.
If velocity is negative, why do you get 2 mvr and not 0?
Because r is also negative. R for this guy is also negative.
Is r a vector?
Yep. Everything's a vector.
I thought it was a distance, so
It is a, it's a
Isn't-
distance to the left. It's got
what's the magnet?
R. All right, let me
Oh,
put it this way. R1 then is negative 1 meter, and R2 is positive 1 meter, right? If you want to do it that way. Although you don't really need to do that, because you could just do it with torque, Lucas, and not even bother giving them signs, right? Does
okay.
that make sense?
Kind of. I'll
All right,
take your
so
word.
let me go back to this then, to make sure you're clear on this. If I have an axis of rotation and I have a mass out here at a distance of 1 meter and it's traveling at 1 meter per second. However, I'm going to say that y is positive up and x is positive that way. So r is negative 1 meter in the x hat, and v is negative 1 meter per second in the y hat. And then L is mvr, sine of the angle between them, but they're 90 degrees off. So this would be, let's say m is 1 kilogram. I know they're all ones, but 1 times -1 times -1 is 1. Over here, if this is our z hat again, r and v, now r is positive 1 and v is positive 1. So either way, they're both going to have MBR is equal to 1 kilogram meter squared over seconds. Does that make sense, Lucas?
Yeah, I was just having a hard time because to me the radius is like positive.
Yeah, and no, you're right. That's why I want to show you this. When you do this torque right here, if you just assume that they're positive, like they're the magnitude of R, that's actually probably simpler. And the reason why is we're saying that L is MVR, right? But V is in the Y direction here, X is in the, or R is in the X direction, and L is in the Z hat direction. So if you get really bogged down in these direction rules, you're going to mess yourself up so bad because it's a cross product. So what I find is easier is just to draw the torque diagram and make sure I rotate R to the momentum for angular momentum.
Yeah, and alpha or omega will be positive, right?
Right, and
So
they would both have positive angular momentum because their angular momentum vector would point in the positive Z hat direction.
yeah,
Yeah,
right.
it's
Okay.
it's a huge pain. I'm not going to make you guys do this. Just so you know, there's like 12 problems in the book where they give you a couple particles and they want you to do unit vectors for angular momentum. I think it's useful to do those if you have a chance, but I'm not going to force you to. Just know that angular momentum is a vector, and you'll see that soon. The cool thing about angular momentum is that no torque. So torque is d dt of L. Are we sure? Remember that torque was I alpha? Well, L is I omega, and we assume I can't change. So I becomes d omega dt, which is I alpha. So our torque actually has a Newton's second law equivalent. Torque leads to a change in angular momentum. That, you guys, is, again, I said it before about momentum, that's the secret to understanding everything. And I'm going to show you how right now. But if there's no torque, there's no change. That means that momentum, angular momentum, is conserved. So we're going to talk about a couple of different examples of this. Have any of you ever watched a figure skater and you see that they spin around really fast? And what they'll do is they'll kind of tuck themselves up into a ball and they'll spin super fast. And then they come out of it and they throw their hands out and they slow down or stop. If you assume that the ice is frictionless, there's no torque from the ice. So their angular momentum can't change. Now, if we assume that's true, then what we get is I initial, omega initial is I final, omega final. If you can change your moment of inertia, you can change your speed. And that's exactly what happens. So let's say she's got her arms out. And I know she doesn't look like a figure skater, but she's spinning around with some omega. And her I is 23 kilogram meters squared. And then she tucks into a small ball and she spins faster, but we don't know what this is. And her I in this position, because she's tucked in, is almost half of what it was. So what we write is we write I initial, omega initial is I final, omega final. If we want omega final, that's simple. I initial over I final, omega initial. Now that's 23 over 12 times, if she was initially rotating at 4 rads per second, 4 times 23 divided by 12 is 7.6. So omega final is 7.67 rad per second. By tucking in, she increases her speed. If you look at people who do diving, the reason why diving is a big one is once you leave, the platform, you can't generate a torque, right? But what they can do in the dive is they can tuck into a ball to make themselves spin faster. Why does tucking into a ball make you spin faster? It makes you spin faster because your angular momentum stays the same, but your moment of inertia changes. So if you can make your moment of inertia smaller, you'll slow down. Now, here's the funny thing about this. You guys already know this. You may not know you know this, but have you ever tripped? What's the first thing you do when you trip? You put your hands out to steady yourself, right? If you're like walking on something slippery, what do? You put your hands out to steady yourself. Maybe you put your hands out to stop yourself from hitting face first into the ground. But in general, when you walk on a tightrope, you put your arms out. Why? What's the point of doing that? Well, the point of doing that is,
Balance.
no, you're changing your moment of inertia. You're actually making your moment of inertia bigger. I'm going to show you that right now. This is in your book, and it's in almost every physics book. You can look this example up. But imagine that you're holding a brick, and each brick has a weight of 2 kilograms. So you're holding a brick in your hands, and they say that this is like the college professor or whatever, but I always find that stupid, but I put it on here because it's what's in the book. Let's say that how long is your arm? I don't know. My arms are, I don't know how long my arms are. Let's say that they're 0.66, 66 centimeters. So you start off and you're going around at 4 rad per second, right? Your body's moment of inertia, let's say, is 25 kilograms meters squared. But these bricks you're holding out, each one, if we assume that they're a particle and we're holding them out at r is that, we get 2 times 0.66 squared. What is this? 0.8712. So my I initial, omega initial, this is my L initial, is I of me plus I of the bricks, but there's 2 of those, times omega initial. Now, let's say for I final, I'm going to pull the bricks into 0.02 meters. So I'm going to tuck them in. So I final for the bricks is now going to be 2 times 0.02 squared, which is 2 times 0.02 times 0.02, 0.0008 kilogram meters squared. All right, and I for me stays the same. Okay, so this initial one would be 25 plus 2 times 0.8712, and that times 4. My L final would be I final omega final. So that would be I me again, plus 2 times I bricks where they're closer, omega final, which would be 25 plus 2 times 0.0008 times omega final. I can set those 2 things together to find what my final speed is. So my final speed, I'm just going to multiply these out without doing all that. So 25 plus 2 times 0.8712 times 4 is 107, let's call it, divided by this side, so 25 plus 0.0016 is about 25. And so 107 divided by 25 is about 4.3. Not a lot, right? I only increased my speed by 0.3 radians per second. But these numbers I just threw up on the board. I just made these up out of my head right now. You can actually, and this is really cool, if you have a chair that you can rotate on, if you guys have a bar stool at your house, we actually have some chairs that will spin in lab which it totally sucks that we can't, but you can actually try this by spinning someone with their hands out, have them tuck it in, and they'll speed up. The idea here is that the angular momentum, I and omega, stays the same, the total of it. It's conserved because there's no net torque acting on you. There's no outside torque. You're just moving stuff into your body. Does it cost energy? Yes. Your muscles have to be able to pull things in and hold them there. But basically, you can increase your speed. Or conversely, I could start spinning you with 2 bricks in your hands and you can put them out and you'll slow down. When you trip or when you're trying to balance, what you're doing is you're trying to get as much weight away from your center, your axis of rotation of your body so that it's hard for you to fall over. Try it, think about it. That's actually what we as human beings instinctively know to do. If you start to trip or start to fall, you put your hands out and you maybe stand a little wider if you can. This is also why if you see someone walking a tightrope in like a circus, they'll have a really long pole. The reason why they have the really long pole is essentially it makes it harder for them to rotate. And therefore they can walk on the tightrope and make minute adjustments instead of major adjustments when they start to tip one way or the other. It's pretty cool. Pretty weird, but pretty cool. One other sample problem that I don't know why they do this in every physics book, they'll talk about a cockroach on a spinning wheel. And there's a sample problem in your book. So imagine this is like a pottery wheel and there's this big cockroach at an initial radius of 4 centimeters, and then it's going to move out. And the mass, the wheel itself has a moment of inertia of 46 kilometers per second. It's initially spinning with omega is equal to, let's say, 2 rad per second. The cockroach has a mass of 1 kilogram. It's a huge cockroach, and it's going to move out. So I initial, omega initial is I final, omega final. I initial will have to be I of the wheel plus I of the cockroach. So this is 46 plus what is I of the cockroach? Well, if R is initially 0.04 meters, then this is I C is mr squared, which is 1 kilogram times 0.04 times 0.04, so 0.0016. So 0.0016. And if it's initial spinning at 2, then L initial is 46 plus 0.0016 times 2. If I can, 46 plus 0.0016 times 2 is, nope, I'm done. 46. 92. Whatever this is, kilogram meter squared over second. All right. Now, if big R were, let's say, 1 meter, so I final for the cockroach becomes mr squared, which is 1 kilogram times 1 meter squared, which is 1. Then L final would be 46 plus 1 times omega final. And that would equal 47 omega final. So we have I initial, omega initial is I final, omega final, omega final is I initial over I final times omega initial. But I know that that's already 92 over 47, which is 1.96 rads per second. Why did it slow down? Well, it's because if the angular momentum is the same and the angular momentum is mvr, if r increases for one of them, then b has to decrease, or omega has to decrease if r increases. It's kind of weird to think about, but it's exactly like putting your arms out slows you down. This mass moving to the edge actually slows down the entire thing. There's one other thing to talk about, and that's collisions. We can have rotational collisions inelastic. So remember, in an inelastic, ball one going towards ball two, they stick together and they both travel away. In your car's transmission, there's something called gears, and we're going to say that this is a drive gear, and let's say it has mr squared over 2, and it's initially traveling at 100 rad per second, right? And there's a second plate behind it called a clutch plate that's not moving. It's got nothing to do with it. Then we drop that clutch plate on there. So now they're working together and they're spinning together, the clutch and the drive plate. And let's say that the clutch plate has the same mass, but R is equal to half of this one. So R of D is 2 meters, and let's say R of C is half of that, so 1 meter. And they both have the same mass of 20 kilograms. So I initial, omega initial is equal to I final, omega final. And we want to know what omega final is. So I initial is just I of the drive plate, because C is not moving initially. And then these guys are rotating with omega final. So I initial would just be 20 times 2 squared over 2, which is 40. I final would be the two of them together. So it'd be 20 times 2 squared plus 20 times 1 squared. So this would be 40 plus 10. So this would be 50. And so we get omega final would be I initial, omega initial over I final, which would be 40 over 50 times 100, which is 80 rad per second. In your transmission, that's kind of what slows down your transmission if you shift to a lower gear. You actually generate more power. Your book talks about power associated with this. Don't worry about power associated with angular momentum. It doesn't come up. But in this case, you can have inelastic collisions where they stick together, and the initial angular momentum and the final angular momentum are conserved because we considered the system to be both of them. That's a little weird, but it's totally true. So out of all this angular momentum stuff, the big takeaway is always we're talking about rotation around some axis, which means we're talking about angular momentum around some axis. The last thing that I really want to talk about is what's called a gyroscope. I want to go to a video and let you guys watch a 5-minute video, and then I want to talk about it with you and talk about how it works. This is a little crazy. If you don't know what a gyroscope is, this might kind of blow your mind. But essentially, what he's going to show is you have a rod that has a wheel attached to it, and this thing can spin, right? So it can spin that way. If it's not spinning and you attach that rod with this wheel on it, it just falls down. Why? Because the force acting on it is mg, and it's acting at a distance r, and so obviously, right, that's going to cause a torque, which is just going to cause the wheel to fall over. It's going to rotate down and drop. However, once this wheel starts spinning, which you'll see, once the wheel starts spinning, it will just sit there and go around and around. So it'll rotate around and around without falling over. Is it anti-gravity? See if you can figure out what you think might be going on here. And then we'll talk about what's going on. And we'll talk about why we care. It turns out that these are used in everything. Don't want that one. I think this might be it.
Grammarly can help you write quickly and confidently, so you never have to slow down at work. Instant.
Let me see if I can get that. Oh, I know why I'm doing that. All right. All right. Sorry. Being dumb. Okay. It's a short video.
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel.
So
The first thing I notice about the spinning gyroscope is that it resists attempts to change its position.
So actually, if you have a way to get a hold of like a bicycle tire and try this, it actually works. If you're spinning, we have these bicycle tires that have handles that it'll spin free of the handles. You get this thing spinning and you hold it upright and try to turn it to its side, it will fight you. It's weird. You can actually feel the angular momentum vector.
First thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope
It's
upright.
not creating a force.
When the wheel stops, the force disappears and the gyroscope falls.
Okay, maybe it's creating a torque, maybe a force.
Incredibly, this force will support the gyroscope like this.
This
It
is
appears to be
another-
levitating.
All right. So anti-gravity or what? Let's talk about this. So when that wheel's spinning, right? Any wheel. So what you're doing is you're kind of looking down on it. So imagine the wheel looks like this, and since it's spinning this way, by the right-hand rule, omega is along this z, but L or big L, whichever one you want, is also along that z. When it rotates, the angular momentum vector points along positive z, okay? Secondly, if you look at the whole apparatus, there is a radial vector from the point of suspension, and there is a weight, mg. These two together, R and mg, do form a torque. By your right hand, you can see that if you push R down to mg, it goes in. So looking down, we have this torque due to R cross mg, and we have this angular momentum vector pointing out. And so what happens, because it's spinning, it has that angular momentum vector. The torque actually makes the wheel start to move. And what we say is, since this thing's going to go around, this change of angle with time is something that we call precession. So we have a bunch of doubled up things here. We have omega, the wheel, and we have R, and we have mg, and we have a force, and we have L and L. But to try to make the most sense of this, essentially what we have is looking down from above, we have this wheel and it's rotating, with omega. So you have L pointing outward. But looking at it from top down, I have mg and I have R, and so that means that there's going to be a torque trying to push it around. Remember, torque is change of L with time. So if this thing moves slightly, just slightly, okay, this will be dl, this will be L, and this will be L, and this will be some change of theta. Now, remember S is R d theta. We did that. So here, this would be dl is L delta theta, or I'm going to really call it infinitesimal theta. So d theta is L over dl. If I divide this by dt on both sides, what I get here is I get, why do I have that flipped? Yeah, I do have that flipped. Sorry, this is dl and this is L. I'm like, wait. Now, remembering that dl dt is the torque, but the torque here is mgr, right? So d theta dt is dl over dt times 1 over L, which is mgr. What is L? L is I omega of the wheel, and I for a wheel is mr squared over 2, and omega is b over r, but let's leave it as omega. So if I put mr squared over 2 times omega here, what I get is d theta over dt is g to r omega. This thing right here is the rate at which this gyroscope spins around the pivot. Notice that it depends on, the bigger r is, the slower it will spin. This is called a precession rate. The faster the wheel itself is spinning, the slower it will precess. But also, if we know the precession rate, and they usually call it this omega term, if we multiply that by r omega and divide by 2, we can find g. So in a machine, if you had one of these gyroscopes spinning and it didn't have friction at the pivot point, it would spin forever. And you could find g by knowing the r distance, how fast the wheel was spinning, and how fast it was precessing around. That's one use. It's not the best use. The best use I'll show you in a minute. Once the wheel
A
slips,
spinning gyroscope will balance
it
on
will
a
fall
string.
over. But it'll also spin faster as it slows, which is weird. But
You can even lift the gyroscope with a string looped around one end.
so my question to all of you right now is this thing defying gravity? Is it anti-gravity? The answer is no. Gravity is actually providing the precession. The force of gravity is torquing it so that it's much like a projectile is falling around the earth. If you shot something fast enough, it would never hit the ground. It would always fall around the earth. This torque is causing this thing to always spin around so it can never fall over. Really weird stuff.
This interesting behavior is difficult to explain.
It's not that difficult.
Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has.
True.
To change the direction of the stone requires a force. Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation.
And it does. And that's
The
because
fact
of,
that gyroscopes will maintain a particular
because of conservation of angular momentum and the lack of external torques. If there was friction at that pivot point, it would slow it down. It would provide a torque. It would make it fall over. So you need a frictionless pivot point. The coolest part of gyroscopes, though, how many of you use your phone to look at a picture and you flip it? You turn it from upright to sideways to see like a long view. You might wonder, how does your phone know which way you have it oriented? Well, it's got these little gyroscopes in it that are in little sensor cages that are spinning, and they always stay aligned to G. They always align themselves in the same way that I showed you to G. So angular momentum and G are always aligned, and it never changes. They just sit there and spin like that. When the phone moves, changes orientation, these little sensors get moved. The gyroscope stays spinning exactly how it is. The sensors on the phone change. And so when it's picking up different sensors, it knows which way your phone is angled, tilted. It doesn't have liquid in there. An old way would be like a liquid mercury switches or something, but it doesn't need them. It has micro gyroscopes that are spinning aligned to the Earth's gravitational field, and that's how it knows. This same thing can be used in an aircraft to tell an autopilot which way to fly, if the plane's level or not, and the plane can level itself out using gyroscopes. They're used in satellites. They're used in almost everything. If you just like look up by gyroscopes online, or what has gyroscopes in it, you're going to find all sorts of cool things. And gyroscope, I don't want to read through all this, but they have 181 different gyroscopes for sale for different robotics, for just any instruments or machines that you need to know their orientation. Gyroscopes are really cool, and they do seem to be defying gravity, but they're not. What it is that instead of gravity causing it to fall, gravity's causing it to spin, and that's really weird. But it has to do with angular momentum and how conservation of angular momentum works in the absence of external forces. It's a little weird that the faster the wheel spins, the slower it precesses. So the bigger this number is, the slower it goes around. The bigger the radial arm is, the slower it goes around. But you can also use it to find G, because it is aligned to G, which is kind of weird. So in satellites, they have to make sure that they get the right value for gravitation, gravity acceleration. Anyway, so I'm going to go back to homework in a second, but next week we're going to do equilibrium, stress and strain, and putting it all together stuff. Today I'm going to post, as soon as we're done here, I'm going to go post practice exams with solutions. And then we'll start going through review even on Tuesday next week. And then on Thursday, we're going to have a lab that's not too bad on static equilibrium. So we'll hopefully be putting it all together next week. And then we'll even have review. So we'll have some review on Thursday, and we'll have some review on the following Monday too, or Tuesday too. Okay, so make sure you got your quiz done. Make sure you're getting your homework done for 10 and 11. But I wanted to talk about a few of these other problems. We already talked about this. You just need to remember to keep energy in there. This is a yo-yo. go through the yo-yo thing. A sanding disk, the angular momentum, remember, is I omega. So make sure that you understand what these concepts are. That is not a hard problem at all. Here, this is like the professor problem. So you're going to need to find his moment of inertia and how it changes, or how his final speed changes by how he moves these bricks. That's not a tough problem either. Rotational star then collapsing. If I changes to 1/6 of its initial value, what is the change in kinetic energy? So remember, if inertia is conserved, I initial, omega initial is equal to I final, omega final, you're going to need to then get the change I omega squared over 2 for final minus I initial omega initial squared over 2. Not too hard, just do it and see what the numbers indicate. This problem is a inelastic collision with angular momentum. Okay, so when you do this, you just need to make sure that these things rotate together. It's not too bad. I'll let you try it and we can discuss it next week. But I don't think it's really that bad. This problem is kind of cool. Now, in this problem, the rod is swinging and the particle is swinging counterclockwise, and the particle is traveling straight down. So what's got to happen is their angular momentums have to cancel out, which means the angular momentum at the point where the red particle is would be MVD for that particle. The angular momentum for the rod will be I omega squared, or I mean I omega. So you're just going to have to figure out how those things work. But they're going to cancel each other out. So, and then there's a quick question on that you can answer. Not too tough. This problem is horrible. So since you're all still here, this will at least save me a little bit of time. Ignore this. What they're saying is that the ball is traveling at, what did it say? So at 9 meters per second at an angle of 0. And then they give you this weird angle. So what they're saying is you're on a merry-go-round and someone throws a ball to you and the ball travels straight to you. It doesn't travel at this weird, stupid angle. So what you need to do is treat it as a collision with angular momentum, okay? So what that means is find the angular momentum before the collision and the angular momentum after the collision, and it's not too hard for that. I initial, omega initial, you need to get the ball and the child, and then I final, omega final for the ball and child together. So you're going to need to find their moment of inertia afterwards. It's not too bad, actually, but for whatever dumb reason, Wiley made this look like it's at an angle, and then they tell you it's not at an angle. So the child is just before the ball is caught, the horizontal velocity is 9 with the line tangent. Yeah, so initially the angular momentum is just the ball, m of the ball, v of the ball, r to the child from the axis. And then afterwards, they want to know how fast the child's rotating. But remember that now afterwards, the child and the ball together are I, plus the merry-go-round's I, times I, or omega final. Not too tough. And then question 10 was the one I explained, that you're going to have to start by moving the axis of rotation and then solving it So go back to that part of this video and review it if you need help on that, if that doesn't make sense to you. And we can, of course, talk about it next week. So that's all I've got. I got vaccinated. If you can get vaccinated, go get vaccinated. If you already have, you're awesome. I'm going to go try to rest my arm. I'm getting really stiff. So anyway, if anyone has any questions, let me know. Otherwise, we're done for today.